of this lecture, we have covered what is corrosion, what are its types, what is the chemistry of corrosion, and how we can remove corrosion. In the next part, we will study what is metallurgy, how metallurgy can be understood in terms of Ellingham diagrams, and the thermodynamic aspect of it. Hello students, I am Dr. Upasna. To know more about this topic, you may refer to the book by S. Chand Publishing, the e-book link of which is given in the description box. Thermodynamical aspect of reduction process. In metallurgy, we know that the metal can be extracted from its ore by various chemical treatments. So if it is present in as oxide, we have to reduce it to get it in the metal state. So the first of this was proposed by Ellingham through Ellingham diagram, which represents the dependence of standard Gibbs free energy of the formation of metal oxides and is used to identify temperature at which reduction by carbon or carbon monoxide takes place. So basically, how thermodynamics can be related to metallurgy. Ellingham suggested that there has to be a certain temperature at which the reduction reaction can take place, or the temperature at which formation of those oxides will take place. So the choice of reducing agent for the reduction of metal oxide can also be seen from the Ellingham diagram. We know from the thermodynamics that Gibbs free energy change for a chemical reaction is delta H minus T delta S. If we make the reaction for formation of metal oxide, it is metal solid giving oxygen as well and forming metal oxide solid. This reaction is the basis of the formation of metal oxide. We can see that the energy here is negative, or it is an exothermic reaction. So delta H is negative. What is delta S? This is solid, this is gaseous, this is solid. Entropy of the system is decreasing. A gaseous species here in the reactant, and in the product you don't have any gaseous species. So delta S is negative for this reaction. According to thermodynamics, if I have first parameter negative, second parameter T minus T into minus of delta S, that means this parameter becomes positive. So I have minus of first parameter plus of second parameter. That means as you rise the temperature, the reaction becomes less negative, or in other words, delta G becomes less negative, and ultimately it approaches a zero value and then it becomes positive. So the temperature at which it remains negative is the temperature we have to consider for this particular reaction. That means I can say that the reaction is spontaneous only up till a certain temperature range. The G becomes less and less negative with rise in temperature. So this is the Ellingham diagram. Now Ellingham diagram is simply the representation. If I just explain you like this, dg is equal to delta H minus T delta S. So the differentiation of dg delta G, change in this with respect to temperature, is your diagram, that is Ellingham diagram. And in this Ellingham diagram, we have the representation Gibbs free energy. Here it is negative, and here this mark is the zero Gibbs free energy. That is, equilibrium is established, and above this the reaction becomes non-spontaneous. So this is spontaneous, non-spontaneous, and these are the temperature at which it is existing. So the slope of this gives you the entropy of the system. This diagram is made for different metals and its transformation to its oxide. For example, this line represents calcium and calcium oxide reaction. This line represents magnesium and magnesium oxide reaction, and so on. What are the salient features of this diagram? Number 1, it talks about conversion of metal and metal oxide at any temperature. The points here, as you can see, represents a break in the slope. Initially, the slope is increasing as the temperature is increasing. So, the first point here is that as the temperature is increasing, your delta G is becoming less and less negative. That means it is going towards positive direction, and when it is going, the slope is increasing. What happens at this point? At this point, the initial conversion was happening from the solid state. Solid metal getting reacted with oxygen to form metal oxide. If the transition points come for the solid, if it becomes liquid or it vaporizes, at that very point, then liquid will react with oxygen, or gaseous species, vaporized species will react with oxygen. So this break represents the transition of solid metal to its liquid state or to its vaporous state. Next point important here is that if we see the curves for mercury or for silver, we see that it is crossing the zero line. That means that for mercury, beyond this temperature, the conversion from mercurous oxide to mercury is spontaneous and not the other way around. The backward reaction becomes spontaneous and not the forward reaction. So during the metallurgy process, our aim is to get metal from the ore. So because for these metals, mercury and silver, the temperature is attainable. For other metals, you have to increase the temperature to such an extent that it then goes beyond zero. This is not an easy task. So for mercury and silver, this is attainable, and hence we say this part of the metallurgy as pyrometallurgy, that only by heating we can get silver or mercury or gold from its ores. These are some of the salient features of Ellingham diagram. Fourth important point here is that one metal can act as reducing agent to the other. So just like electrochemical series, if calcium to calcium oxide Gibbs free energy is more negative in comparison to magnesium oxide, so if we take these two together, one will act as oxidizing agent and other will act as reducing agent, or in the combination only one reaction is spontaneous, that will be this, and magnesium formation will take place from magnesium oxide. So these are some of the important features of Ellingham diagram. The last but not the least feature is this line. This is the only special line you can see in the Ellingham diagram that represents a negative slope. A negative slope indicates that here what is happening? Initially it is carbon solid to oxygen forming carbon dioxide, and then you have carbon plus oxygen forming twice of carbon monoxide. What happens in case of carbon? The Gibbs free energy change is opposite as compared to other metals. This is a non-metal carbon which is showing a different trend. So the application of this is that carbon can be used as a best reducing agent in comparison to other metal oxide conversion, and this is the property. So in this topic we have learned about the corrosion, the effect of corrosion, types of corrosion and how it can be removed, and also we have covered the theory behind the thermodynamics of the reduction process and the Ellingham diagrams. To know more about this topic, you may refer to the book by S. Chand Publishing, the ebook link of which is given in the description box. If you found this video interesting, please like, share and subscribe the S. Chand Academy channel. Also, don't forget to press the bell icon for getting future updates. Thank you.
without the permission of the copyright holder.